Hello everyone, thank you for coming to my presentation. My name is Louis Bondurant, and today I will be discussing variations in lignin content that have been deposited in the Congo Fan and the potential for oxidative camouflaging of terrigenous organic matter that has been deposited in marine settings. So before I get talking about the work that me and my group have been doing, we first need to do a little bit of background information. So first, what is organic matter? So organic matter is carbon-based material that is derived from living organisms, and it can be broken down into a variety of different classifications. One such classification is based on the source material, where you have three main areas of where organic matter can originate, being terrigenous, primarily coming from land plants, lacustrine, originating from freshwater algae, and marine, coming from oceanic algae. Organic matter is a highly complex heterogeneous mixture which makes it difficult to characterize by normal analytical means. So instead, organic geochemists look at organic carbon and their specific biomolecules. So why is organic matter and organic carbon important? Well, carbon controls the global climate that we all experience in our day-to-day lives, and understanding the flow and storage of carbon throughout the environment is important to understand environmental changes that may happen to our Earth. Additionally, we have a conundrum that has been facing the organic geochemistry community for over 10 years, and that is that more terrigenous organic matter is input into the oceans via river transport, so approximately 157 teragrams of carbon per year, compared to what is observed, which is less than 50% of this terrestrial or terrigenous organic carbon is found in marine sediments, and that is generally confined into the ocean of coastal regions. So the conundrum is, where is this terrestrial organic carbon going? And that's what we're hoping to answer with the research I'm presenting here, as well as future work that our lab is currently working on. How do we, as researchers, distinguish between terrigenous and marine organic matter? There are a few ways. One is looking at the stable carbon isotope ratios, or delta 13C. So terrigenous organic matter, by way that land plants fix CO2 into biomass. This leads to a delta 13C value that is depleted in 13C with values typically less than or equal to negative 28 per mil, while marine organic matter is generally observed to range from negative 20 to negative 22 per mil. Another method to distinguish terrigenous from marine organic matter is by looking at molar carbon to nitrogen ratios. The difference here is due to the presence of proteinaceous material in marine organic carbon compared to terrigenous. So terrigenous organic matter generally has a C to N ratio uh, at or above 12, while marine generally ranges from 6 to 8. And the last that I'll be discussing is looking at biomarkers, so specifically lignin as a biomarker for terrigenous organic matter. So just a little bit of background. Lignin is a biopolymer that is found in the cell walls of vascular plants that provides structural integrity to the plant. And its structure varies based on the plant type and environmental conditions, but here to the right we see a generic structure of lignin, and we see that it's rich in aromatic oxygenated subunits. So now on to the work that we will actually be discussing today. My work focuses on samples from the Congo Fan, which is supplied by the Congo River, which is the second largest watershed in the world and has been estimated to deliver about 2 teragrams of carbon per year of particulate organic carbon into the ocean. This exported particulate organic carbon is transported through the river and out to the deep ocean through a submarine canyon channel. So that's what this looks like here, where we have the mouth of the Congo River would be originating right here, which enters a high level of erosion canyon area, which is around 300 kilometers long and extends out to 800 meters depth, and then kind of transitions into a channel, which is an area of less erosion that is another 600 kilometers long and extends out to 5,000 meters depth. This canyon channel system terminates at an area called the distal lobe. This is an area where we have high amount of sedimentation and is believed to be anaerobic. And it's been estimated that 33 to 69% of Congo River terrigenous particulate organic carbon is deposited in this lobe complex. So here are the specific samples that I'll be discussing today that we have collected. So we have 3 specific ones from within the canyon system at that distal lobe, and then off to the side, not within this canyon channel system that is termed the abyssal plain. And we see that the distal lobe and the canyon samples have a relatively high amount of carbon compared to what is typically observed in abyssal depth ocean sediment samples. And that the delta 13C values for both the distal lobe and the canyon are at or around that value that is typical of terrigenous organic carbon, compared to the abyssal plain, which is within that region that would be classified as purely marine organic carbon. So because of the low carbon contents that we observe in these original samples, we decided to do hydrofluoric acid treatment to concentrate the organic matter. Due to the planned experiments that we were going to do, we deemed that these low organic carbon concentrations were too low to be useful in some of our analytical procedures. So following that HF treatment, we see a minimal change in the delta 13C values compared to before HF treatment. However, a great increase in the amount of organic carbon content following that HF treatment. And then we do see a slight concentration of nitrogen content, which suggests minor loss of carbohydrates. But I'll be showing some data using solid state NMR that shows that we still have an abundance of carbohydrates within these samples following HF. So that's what we are showing here. So this is solid state NMR spectra of the abyssal plain, distal lobe, and canyon samples. And specific regions of these spectra can correspond to specific functional groups within organic carbon. So here we've got aliphatic carbons, which are at 30 and 33 ppm, which correspond to amorphous and crystalline aliphatic compounds respectively. This can originate from compounds such as fatty acids found in the sediments. Next we have at around 72 and 105 ppm corresponding to hydroxy and anomeric. These are common functional groups found in carbohydrates. And then lastly we have peaks at 56 and 154 ppm that correspond to methoxy and aromatic oxygen subunits. And these peaks correspond to that of lignin. And in the distal lobe and the canyon sample, we can see the abundance and clear peaks that are associated with that methoxy and aromatic O, as well as just aromatic carbons. And then due to the signal to noise ratio of the abyssal plain being much lower than these two, it's kind of ambiguous as to whether these peaks correspond to lignin or some other functionalities within these sediments. So we can use these spectra and integrate over these regions and get estimations for the biomolecular composition of these sediments. This is using a mixing model that provides estimates, as I'm saying, of different biomolecules such as proteins, carbohydrates, lignins, lipids. And using this, we get estimated lignin contents of these samples and see that the abyssal plain has 0% lignin, while the distal lobe and the canyon have around 15% lignin. To confirm the presence or absence of lignin, we use tetramethyl ammonium hydroxide thermochemolysis, or TMAH thermochemolysis. This is a process that breaks down the large lignin biopolymer into monomers and methylates them using heat and pressure and tetramethyl ammonium hydroxide. And this breaking down and methylation these compounds are now able to be analyzed using gas chromatography. So that's what we're looking at here. First, the distal lobe and the canyon samples. And I know there's a lot going on here. The things I want to point your attention to are the G-labeled compounds, the P-labeled compounds, and the S-labeled compounds. These are all specific lignin monomers that are observed following this TMAH procedure. So this is basically showing us that both the distal lobe and the canyon samples have lignin present within them. On the flip side, if we look at the abyssal plain sample, we see no presence of those lignin monomers present. There's also a method of quantifying lignin, and that's based off of 8 specific lignin phenols, and that's on a carbon basis of every 100 milligrams of carbon. And quantifying these using GCFID, we see that this lambda 8, that's sum of 8 lignin phenols per 100 milligrams of carbon, there is 0 within the abyssal plane, and then 0.18 and 0.14, which correlates slightly with the estimations from the solid state NMR percentages. So with all that, we have confirmed that there is lignin input into the abyssal depths of the Congo fan system at that distal lobe, and that there is no apparent lignin present in the abyssal plain region. So this could be due to one of two factors. One, that there is no input into this area from the Congo River. A second is that the terrigenous organic matter could have been degraded through some oxidative process so that we can no longer observe that lignin biomolecules, and we see values of isotope ratios of delta 13C within the marine region. So we decided to perform a laboratory oxidation of the anaerobic distal lobe sediments. This is done using Fenton's reagent. So Fenton chemistry uses ferrous iron or iron 2+ and hydrogen peroxide to form reactive oxygen species, which are a very strong oxidant for organic matter, and have been shown to be able to degrade carbohydrates, proteins, and even lignin. So the experimental method that we used is about 0.5 grams of the HF treated sediment was loaded into vials. This was mixed with 60 ppm of iron 2 and 0.5 molar hydrogen peroxide. And each of these were allowed to react for 1 day before freezing to halt the reaction, drying using freeze dryer, and then replenishing the hydrogen peroxide to continue the reaction. And this was done for a total of 9 oxidation time points and 1 control, ranging from times from 1 hour up to 8 days of oxidation time. So looking at the elemental parameters following this oxidation, we see a major loss of the organic carbon content as we increase the oxidation time, corresponding to about 64-63% carbon loss. We also see the initial delta 13C value of around 26.8 goes down to a value of negative 21.6, transitioning from a more terrestrial delta 13C value to a more typical marine value. Similarly, the carbon to nitrogen ratios transitioning from what would be termed a terrestrial value or terrigenous value, transitioning into a more typical marine value. So looking specifically at the organic carbon loss, as I said, we see around 63.1% of carbon loss after 8 days of oxidation, and this is likely due to the production of CO2 or CO produced during the oxidation that are outgassed. And the best fit that we obtained was using the power law, which is this equation here, which is commonly applied to marine sediments. And it shows the variation in the degradability of the organic matter with a rapid degradation at the early onsets and then a sort of slowing of that degradation as we extend the oxidation times. Looking at the carbon to nitrogen shifts, again, you see a value starting at what would be termed as terrigenous range of 16.6 and terminating down into a typical marine value of 6.5. We got best fits for a 2-component exponential decrease, and further showing that the oxidation of these sediments transforms them into something that would appear of marine origin by traditional means. And then lastly, the isotopic changes that we observe. So again, the initial value of negative 26.8 per mil is typical of most terrigenous plants, and then terminating at a value in between negative 22 and negative 20, which is what is traditionally termed as of pure marine origin. So the shape of these this curve implies a mixing of labile and recalcitrant fractions, or FLB and FR. So we decided to use two-component modeling to better understand the kinetics of this isotope enrichment. And so to do that modeling, we use this long equation here that breaks up into labile and recalcitrant fractions. And if you have any questions about this, I'm not going to get into it right now, but please feel free to ask me and I can explain it to you. So applying this model, we get some solutions. We vary the KIE, or the kinetic isotope effect, to be constants of 1, 2, and 3. All of the model solutions produce high R squareds and low error costs, which correspond to errors of less than 0.1 for each point here. And then we get labile and recalcitrant fractions estimations here, corresponding to about 47% of this organic carbon is labile, which would indicate that some oxidation occurred prior to collection. That would be during its transport from the Congo River, during deposition in this distal lobe. Less likely would be after deposition due to the anaerobic nature of these sediments here. The initial labile component of this, the delta 13C, is highly depleted, so negative 31, negative 32 per mil, compared to the recalcitrant portion, which is greatly enriched and typical of that, what we term pure marine organic carbon. And then looking at the solid state NMR, at some of the time points following this oxidation, we see a major loss of these carbohydrate and lignin-like peaks and a relative increase in the aliphatic components. And this spectrum here at the final 8 days of oxidation mimics what is traditionally observed in marine settings. So this potentially indicates the formation of new aliphatic compounds from oxidized lignin, which would be significant. So taking all of this and bringing it all together, we see that the distal lobe sediments are depleted in organic carbon content and lignin-like structures following oxidation. We have a relative increase in nitrogen content and 13C content and relative aliphatic content. And so the terrigenous organic matter found in the deep ocean at this anaerobic lobe system can be what we're calling camouflaged to appear like marine organic matter through some oxidative processes. And so we hypothesize that a majority of what is termed marine organic matter may actually be oxidized terrigenous organic matter that has been transformed and no longer appears to be of terrigenous nature. And if this is the case, this calls into question current global carbon estimations, and would require a re-examination of what we currently have, which would influence our climate models going forward. So with that, I would like to thank you for your attention. I would like to thank everyone at the Hatcher Group and some of my collaborators, as well as the instrumentation facilities at Old Dominion University and Harvard, as well as funding from the Frank Batten Endowment Fund and the National Science Foundation. And with that, I will take any questions you may have. Thank you.